So let's do some more examples. So what's the difference between an inelastic and an elastic collision?
In elastic collision, no kinetic energy is lost.
So kinetic energy is conserved.
In elastic collision.
Yes. So energy is always conserved. Momentum is always conserved. As long as you can track where it goes. If you were to throw a baseball through the air, it is extremely difficult to track the momentum gained by the Earth. Especially if you're standing on the Earth. So whenever you're doing like projectile motion, conservation of momentum is not very useful because you cannot track where all the momentum's going. Because if an object starts falling, that means that wherever object is pulling it down, because of Newton's third law, every action has an equal and opposite reaction, the Earth is also moving up to counteract that momentum. What makes conservation of momentum very powerful is during the brief collision. When two objects collide, there is no external factors in it. It's very easy to contain the system. At the point of impact, the only thing interacting is the two objects colliding. So that means conservation of momentum is very, very powerful when it comes to collisions. But like I said, if I ask you an object falling, you really can't track the momentum gained by the Earth to counteract it, so it's not very useful outside of collisions. Conversely, energy is very difficult to keep track of. Like we did the example of two boxes sliding hitting each other together, and then they stuck. Why do they stick? Well, some of it has to do with sound being generated. We haven't covered how to extract the energy from sound waves, but it's very difficult. Heat being generated by the individual molecules sliding and moving past each other. Bonds being formed. Chemical bonds, when two objects stick together, they attract each other, and there's some electrostatic properties of binding some chemicals together temporarily, and all that is extremely difficult to come over. But momentum during the collision will be conserved because it's a closed system. Some of the kinetic energy may be converted into potential energy, so it's very difficult to keep that in track. But with conservation of energy and conservation of momentum, we can separate these two things. If some object is not colliding or touching some other object, and if we ignore air friction and sliding friction, then it's very easy to keep track of all the energy. If there's a collision, it's very difficult to keep track of the energy losses or energy transformations, but it's very easy to keep track of the momentum. Combining these two, we get a powerful way of analyzing motion. So let's do one more example of an elastic collision. This time, one that's going to require the use of the quadratic formula. So let's suppose that a 5-kilogram box is moving to the right 10 meters per second, and let's make it a 20-kilogram box is moving to the left at 1 meter per second. So this is the before the collision. Afterward, they're going to hit each other and bounce off. That's one possible solution. The other possible solution is they pass through each other. Here's a little fun exercise before I actually begin this. Let's see if you can answer the riddle. Let's suppose an unstoppable object were to hit an unmovable object. So we have an object that is unstoppable, and it hits an object that is unmovable. What will happen? Yes, it will pass through it. That is the only mathematically possible solution. Um, one thing is unstoppable force versus unmovable object is usually the analysis. This exists. For example, a X-ray passing in certain contexts, like an X-ray passing straight through you. You are unmovable by X-rays because you don't absorb them or interact with them, and they can't be stopped by your body. I think your bones can, but you get why my analogy is sometimes light can pass straight through. What's interesting is these two are identical to each other. An unstoppable force is the same thing as an unmovable object, because what happens if you are moving at the same speed as this object? It looks like it's not moving, right? And instead, it looks as if the unmovable object is moving towards you. It's what happens when you're in a car. If you see a stopped object and you're moving a car, it doesn't look like you're moving. It looks like the object's moving towards you. But mathematically, it's easy to see. If this can't be stopped, then the only possible thing is they'll phase through it. So there's two solutions. Either these boxes will pass straight through each other, or they'll bounce off of each other. I'm going to assume there's also multiple ways they can bounce off of each other. For example, let me go back to this. Imagine, for example, that we have a train moving at 100 miles per hour. It's a very massive train. And there is a piece of paper. And the piece of paper is blowing in the wind at 10 miles per hour. What would you imagine would be this, the effect? You would imagine that they're not going to strictly bounce off of each other. They're instead going to be propelled. Or let's make it a ping pong ball. Or, better yet, let's actually do a real scenario. You have a baseball bat that is being swung in this direction, and you have a ball that's flying in this direction. One possible scenario is the bat continues to swing in this direction, and the ball is flipped around in the other direction and moving faster. So this slows down. So this was moving at high speed and loses some of its momentum, and this flips this direction and goes faster. Another possibility is the ball hits and this bounces backward. It now gets swung back, so you hit like a giant brick. Someone throw a brick, you hit it, it bounced backward. But since it's a brick, this is slowed down, so it kind of slowed down the brick. And another scenario is this is swung backward, but the object is moved this way. So we don't know exactly what directions these are in. So you have to guess. It doesn't matter if you're wrong, you'll get a negative value. One thing you could do is just always assume the direction is right. In which case you know all negative values mean left, all positive values mean right. It's up to you. Which way you want to go. To be consistent, I shouldn't say consistent because I'm going to change this up. I'm just going to assume all right. So this is going to move at some final velocity. And this one's going to move toward the right. This way, when I get a negative value, I know they are going to be to the left. Note, when analyzing this, you do need a sign convention. So positive means right. Negative means negative. Left. So when writing the momentum out, the momentum is 5 kilograms. This is pointing to the right, so I use a positive 10 meters per second, plus 20 kilograms. And this is moving to the left, so I'd put in a minus 1 meters per second. On the right-hand side, because I have these all to the right, my variable is going to be put in as positive. One reason why I'm also doing all these to the right is it messes up your sign convention. If I drew this to the left and I put this in as negative, I'm going to get a positive value here. But then it messes up my sign because positive numbers are supposed to be to the right. What I'm doing is already putting in a direction to this number, and I'm no longer signing for direction. To be very rigorous, always draw your final answers or all variables to the right so that you guarantee the number you get is going to be positive to the right or negative. So, to illustrate that problem, let's suppose that the box is moving 2 meters per second to the left. If I come in, and this is a 5 kilogram, if I come over here, I know that the total momentum is thus 10 kilograms meters per second, negative because it's going to the left. If I come over here and put that in, negative 10 kilograms meters per second is equal to, and let's say that I don't know what this velocity is V1, and I put in mass 5 kilograms, and if I go ahead and put that negative in, right here, this negative should be attached to the variable, right? But when you solve this, you multiply both sides by 1, it cancels out the derivative, and you get a velocity that's positive, which can really confuse you when working out mathematics unless you keep track of it. And at high school level, I don't think you've worked enough to do this rigorously. It's hard to keep track, so always put your final results to the right, and later you can correct it. If you get really good at doing physics, you can go ahead and do that and just know that the end is to the left, it should be negative. But keeping it to the right is a simple way of avoiding stupid mistakes. So 5 times 10 is 50 kilogram meters per second minus 20 kilogram meters per second. And 50 minus 20 is 30 kilogram meters per second. It's equal to 5 kilogram V1 plus 20 kilogram V2. So this is one equation, but we have two unknowns. We need another equation, but since we know it's elastic, kinetic energy is conserved. So let's look at it using kinetic energy. 1/2 times mass, 5 kilograms, times 10 meters per second squared, plus 1/2 times 20 kilograms times negative 1 meters per second squared, equal 1/2 5 kilograms times V1 squared plus 1/2 20 kilograms times V2 squared. So this is 250 joules. You'll note that the negative doesn't matter because negative squared becomes positive. This is 10 joules. equal 2.5 kilograms times V1 squared plus 10 kilograms times V2 squared. This is 260 joules equal to 2.5 kilograms V1 squared plus 10 kilograms V2 squared. To make it easier, I'm going to divide both sides by 2.5 kilograms. So divide the whole thing by 2.5 kilograms. A joule divided by a kilogram is just a meter square per second squared. I know this because that's what velocity squared is. So that equals 104 meters squared per second squared. 2.5 kilogram divided by 2.5 kilogram, cancel each other out, give me V1 squared. 10 kilogram divided by 2.5 kilogram is 4. Note the kilograms cancel out. And this just simplifies the equation even more. This step was unnecessary. You could have kept it as this. So now I have two equations, two unknowns. The general strategy for solving this is take one and plug it into the other. This is the most simplest. So I'm going to solve for, let's solve for V1. So I have 30 equal 5V1 plus 20V2. Let's solve for V1. So I subtract 20V2 from both sides. So I get 30 minus 20V2 is equal to 5V1. And then I divide by 5. So that'll be 6 minus 4V2 is equal to V1. I removed units, but we can tell that all these units are going to have to be meters per second. Or I should say 6 was going to be meters per second. But we have one solution for V1. We can take this and plug it into this equation and solve for V2. So we have 104 is equal to V1 squared plus 4V2 squared. So 104 is equal to 6 minus 4V2 squared plus 4V2 squared. So let me flip this paper over. So we have 104 is equal to, let me just write this down. We have 104 is equal to V1 squared plus 4V2 squared. And I have that 6 minus 4V2 is equal to V1. So 104 equal to 6 minus 4V2 squared plus 4V2 squared. We can expand this square out. So 6 and minus 4V2. 6 and minus 4V2. 6 times 6 is 36. 6 times negative 4 is 24. Negative 24. V2. 6 times negative 4 is negative 24 V2. negative 4 v2 times negative 4 v2 is positive 16 v2 squared. So add up all these. This is 36 minus 24 minus 24 is a 48. So minus 48 v2, and then add in the plus 16 v2 squared. Then add in the 4 v2 squared and the 104 here. Simplify further, these two can be added together. And this can be moved over to the right side by subtracting 4. So 104 minus 104 is 0. 36 minus 104 is negative 68 minus 48v squared. And 16 and 4 gives you 20 with the v2 squared attached. So we have a quadratic formula in v2. So this is our A. No, this is our C. If you want to actually move it and rearrange this so it's clearer, we have a 20 v2 squared minus 48 v2 minus 68 equals 0. This is the standard form of a quadratic formula. The square term's coefficient is A. The linear term's coefficient is B. And the constant term is C. And a double check quadratic formula, which you should keep in your notes. We have.
Excuse me, teachers and students, for a quick interruption. If anyone finds a Galaxy S10 has a somewhat of a faded case on it, please turn it into the front office. It's one of our teachers' cell phones was misplaced. Thank you.
So we have v2, whatever a variable is equal to the linear term plus or minus the square root of the linear term squared minus 4 times the quadratic form times the constant coefficient, divided by 2 times the quadratic coefficient. So we have two possible solutions. V2 is either equal to our, let me see if I can simplify this. So minus B, so minus plus or minus the square root of negative 48 squared minus 4 times 20 times negative 68 divided by 2 times 20. So simplifying the radical, the square root of negative 48 squared minus 4 times 20 times negative 68. So this section right here is just 88. So this is equal, and a negative is a positive. So we have 48 plus or minus 88 divided by 2 times 20 is 40. And so now we have two possible solutions. Either V2 either equals 48 plus 88 divided by 40. Which is 3.4 meters per second. Or V2 equals 48 minus 88 divided by 40, which is -1. So, which do you think is the correct solution? What is this -1? Let's look at the original problem. Originally, it was moving with a velocity of -1. So what does this solution correspond to? It corresponds to the possible solution where this box moves through this box. Right? This was the original velocity. So thus, again, you get two possible solutions. Either, another way of looking at it is we're only looking in 1D. This box is moving to the right, and this box is moving to the left, but notice that they don't hit each other. So you can either look at it as this box either passes through it or it misses. But I told you the boxes collide and bounce off of each other, which means this solution is not possible. We can rule this out, which means this is the correct solution. This one corresponds to the box passing through the other one or missing it entirely and continuing to the left. If you were to use V2, what would happen is you would have got a solution V1 equals 10 meters per second, which is the original values. So these are the original values. The case they miss or pass through each other. So using this value, 3.4, we can plug it into this equation here. Actually flip over and we'll go plug it into this equation here. So 6 minus, so V1 is equal to 6 minus 4 times V2, which is equal to 6 minus 4 times 3.4. And we get a value of negative 7.6 meters per second. So our final answer is after the collision. So we have before the collision, this one's moving to the right at 10 meters per second. This one's moving to the left at 1 meters per second at 20 kilograms. After the collision, they bounce, so they hit each other. So collide. And after the collision, this one's moving to the left at 7.6 meters per second. And the one to the right is moving to the right at 3.4 meters per second. One way to double check that this is your right answer is we know that the total momentum before the collision is 30 kilogram meters per second. And we know the total kinetic energy before the collision is 260 joules. Because this is elastic, we can calculate the total momentum on the right. So 5 times 7.6 plus 20 times 3.4, and that gives you 30 kilogram meters per second. That's right. And we can do 1/2 times 5 times 7.6 squared plus 20, or plus 1/2 times 20 times 3.4 squared, and that equals 260 joules, which is correct. One way to double check that you got the right answer. My bad, there is a mistake here. The should be negative. Negative 7.6, because that's negative, or moving to the left. So that's correct. And 0.5 times 5 times negative 7.6, put parentheses around it, squared. So 144.4 plus 0.5 times 20 times 3.4 squared is 115.6. Add those together, and we get 260. Easy way to double check your answer. Let's do a more complicated example. I have a nice picture printed out of it. And let's do what you would do in college. There is 0 numbers in the problem. In college, we usually don't even answer with numbers. It is pure algebra. So, a block begins to slide down a semi-spherical bowl without friction and collides with an equal mass block at the bottom of the bowl. They stick together. How high will the two blocks slide down before stopping? So we have a before. The box is over here. We assume it's at rest. So its velocity is 0 meters per second. I don't think it says it, but this is at rest. Or at least we'll assume it's at rest. That it says right here, begins. Begins means it's initially at rest. Its initial speed is 0. So it slides down, hits this object, and they stick together. So they stick together means inelastic. Kinetic energy is no longer conserved. How high will the two blocks slide before stopping? So how would you solve this? This is very easy. So again, I told you, if you drop an object, let go of an object, it's going to gain momentum. And how, again, momentum is conserved. It can't gain, the total momentum can't change. So whenever something is sliding down due to gravity, we can't really use momentum because we can't keep track of the Earth's momentum. So before the collision, we have no friction, which means we can use conservation of energy. That means the total energy before they collide has to equal the total energy, the initial energy has to equal the energy right before collision. So the initial energy at beginning has to equal energy before collision, right before, the moment they're about to touch. Because no of the energy is being lost. Note, due to it being a inelastic collision. Energy is lost. Energy is converted to heat. Lost during collision. So only during the collision is energy lost, which means before the collision and after the collision, we can use conservation of energy to solve this. So before the collision, we have this scenario. So we have a before. So this will be initial. And right before collision. So all the energy at the very beginning is potential energy. So the entire energy, so the initial energy, is equal to M1 times G. I'm going to call this height right here. No, never mind. Where's the height? What's the height, this distance right here? It's a sphere. So this distance right here is R, right? All distances on a circle have a radius of R. So if I move, so it's a circle. So this would be M1 times G times R. No kinetic energy at the beginning. So all of it is only potential. And this has no potential energy and no kinetic energy. After the, right before the collision, so right before, we have no potential energy. And this block has some kinetic energy. This block is not moving yet. So all of our energy here is going to be in kinetic energy. So 1/2 times M1 times its velocity. And I'm going to call it V1. Right? It's this velocity right before impact. So let V1 be the velocity of first box right before impact. Now, because energy is conserved, that means that M1 G times R has to equal 1/2 M1 V1 squared. We can simplify this and solve for the velocity. So M1 cancels each other out. And we have GR equals 1/2 V1 squared. We can simplify this to GR is equal to V1 squared. And we can move this around. V1 is equal to plus or minus the square root of 2GR. Anytime you take the square root of both sides of the equation, it's always plus or minus. However, note, it will be moving to the left, or moving to the right. Because that's how we drawn. So that means we can ignore the negative and get the solution. So this is the velocity right before impact. Velocity before impact. So now we have the during the collision. During collision. This is conservation of momentum. So we have right before the collision. And we have right after. So we have a box M1 moving at speed of V1, hitting a box M2. And after the collision, they stick together and move at some new speed V2. So the total momentum beforehand, note this has no momentum because not moving. So the total momentum beforehand will be mass times velocity. And that has to equal now that they're stuck together, we have two masses, M1 plus M2, times this new velocity. I can solve for V2 by dividing by M1 plus M2. So I have V2 is equal to M1 V1 over M1 plus M2. Right? So here's our second equation. If you wanted to, you can solve this more specifically. It says here that they're equal masses. I could go ahead and just let this be M divided by 2M. And this ends up with, this would correspond to V2 is equal to M V1 over M plus M, which is the same thing as 1/2 V1. But I'm going to let it be more generic and assume they're different masses. And I can also plug in this into this equation. And let me come over here and solve for after collision. After the collision, nothing is colliding. So this is conservation of energy. How much time do we have? About 2 minutes. So conservation of energy is we have two masses moving at some velocity with no potential energy. And then they move up and stop. So no kinetic energy. Only potential energy. So the initial energy right after the collision would be 1/2 times M1, and this would be V2, plus M2 times V2 squared. And this would have to equal the potential energy on the right-hand side, which would be M1 plus M2 times G times H. Solving for H, we get that H is equal to 1/2 M1 plus M2 times V2 squared divided by M1 plus M2G. Note the M1 plus M2 cancels each other out. M1 plus M2 cancels each other out. So H is equal to V2 squared over 2G. And we know that V2 is equal to this. I'm going to go ahead and do this. So V2 is, so we have H is equal to V2 squared over 2G. We have V2 is equal to M1 V1 over M1 plus M2. And we have V1 is equal to the square root of 2GR. So plugging this into this equation, we get that V2 is equal to M1 times the square root of 2GR divided by M1 plus M2. And plugging this one in here, H is equal to M1 we'll continue it tomorrow. So it should be trivial. All you have to do is plug in, and then you can simplify that they're equal masses. We'll go ahead and give you both homeworks. Yeah, try. I think really just introducing it. All I'm doing this whole week is just doing examples for you. So if you come with a problem you don't understand, ask me about it and I'll do another example on it.